Thanks for inviting me. Today I will talk about a couple of papers, a couple of projects that I have been involved in, and it's about matrix permanence or sparse matrix permanence, and I will describe why it is about sparsity and why I am interested in this sparse matrices only. We also have a study for dense matrices, but this talk will be about mostly the sparse matrices part of this line of research. So permanent, so given an n by n matrix, here in this talk, every matrix will be square. They don't need to be symmetric. But the permanent is computed as in this formula here. So in short, what you do is it is in fact, I mean, when if you want to describe permanent, maybe it is easier to use the determinant formula, because it is similar to determinant, but you don't have the sign on the products. So every sign is positive, so you just sum them. So what you do is you choose one entry from each row and each column. So you choose n entries in total, and for every possible combination, for every possible such combination, you multiply them and add them up, and you have the permanent. So that's the formula. So some applications, well, they are related with Fibonacci and Lucas numbers. There is an application in order statistics. They are related with quantum computing and bioinformatics. So you can find the literature using permanence for these applications. In addition, and this is why I am interested in the permanent, it has interesting relations with graph theory. This is why I am interested in sparse permanence, because the corresponding matrices to the graphs are sparse. So with an efficient algorithm to compute the permanent of a matrix or the adjacency matrix of a graph, you can count the number of perfect matchings for a bipartite graph. So a perfect matching is the set of edges where each vertex appear exactly once as an endpoint of these edges. And for normal graphs, you can find the number of vertex disjoint cycle covers of a directed graph. Unfortunately, computing the permanent of a 0-1 matrix is P-sharp complete. So it is hard even to also approximate. And here is an example. So I have a bipartite graph on the left and the corresponding adjacency matrix just below it. And the permanent for this matrix is 4, because I have exactly 4 perfect matchings on the bipartite graph. And here are the edges, set of edges shown in red for each perfect matching, and the corresponding set of entries for the adjacency matrix is also shown in red. So overall, there are 4 possible perfect matchings and 4 possible set of matrix. They also call it traversals. So this set of non-zeros is also called a traversal. And as you see, there is exactly 1 non-zero on every row and the column of the matrices here. So for a bipartite graph, adjacency matrix is constructed like this. So rows are the vertices on the left, and columns of the matrices correspond to vertices on the right. And I can also add that the white regions inside the matrix, they are 0. And the colored, yellow colored parts, you can consider them as 1. So in fact, this is a real matrix with entries 0 and 1 is a binary matrix. So yellows are 1 and whites are zeros. And this is how you form the analogy between the perfect matchings and the permanent. So when the matrix is not, when the graph is not bipartite for generic graphs, you can form another form of adjacency matrix. Here, rows and columns, they both correspond to the set of vertices in the graph. And again, as before, yellows are 1 and white regions are, white squares are 0. And the permanent for this matrix is 10. And there is one example of a transversal and the corresponding vertex disjoint cycle cover on the right. So this is why I am interested in permanence. I am usually working on sparse computations. I am trying to make them faster, do them in parallel. And we were working on the perfect matching problem. We have a couple of papers for heuristics, for algorithms, for their parallelization, GPU-based, CPU-based. And then at some point, we come up with a relation between a matrix scaling algorithm and perfect matching problem on the bipartite graph. Then we found that, okay, we can use it also for permanent, and we come up a couple of studies also from that line of research. Okay, so so the original equation defines the permanent in terms of transversals, matrix transversals, as I said, and with a naive algorithm, computing the total contribution of all transversals takes n times n factorial time, because there are r factorial such products, and for each of them you need to add them first. Sorry, you need to multiply them first. So you need to do n operations per each. So the complexity comes from that, n times n factorial. But you can do it in a better way. So there is Ryser's algorithm in the literature. So it restructures the original permanent equation and formalize it by using the row sums of the matrix. And by using inclusion exclusion, he came up with this formulation. So here S is a proper subset of the set of rows or the columns. In fact, you can consider them as columns. And then what you do is, so you have row sums on the right-hand side of the formula. So this sum is the row sum, the ith row, and you just compute the row sum for a selected set of columns. You do it for every subset, column subset, and then you just add them up. You just add these products here. So with this formulation, the complexity becomes 2 to the n minus 1 n square. N square comes from the right part of the equation, and 2 to the n minus 1 comes from the summation, the first summation here. But you have this complexity if you do this computation with an arbitrary column set order. So in the literature, there are algorithms which makes this more efficient by using gray codes. So what's the property of a gray code? So it's a binary code. In fact, forgive the terminology if I am saying this, because there is, when I say binary code, I mean that it's a binary value. So 0000, for instance, or 0001. And for each adjacent sequence gray code, only 1 bit changes. So for instance, for the first gray code, it is 0000, and you change the first bit. The rightmost bit is the first bit for me. And then you change the second bit, for instance, and you again flip the first bit, then you flip the second bit, then you flip the first bit again. So only one bit changes. And if you consider each bit here as the column inclusion or exclusion, so let's go back here. So if you want to compute the row sum, you don't need to do it from scratch. You just say that, okay, I am adding a column, I am removing a column. So you just need to update the previous row sum values. And the complexity of this is cheaper. So you don't have n square here again, because for every new set, you do n operations only, not n square operations. So this is the beauty of the gray code here. And this is the algorithm. So you just initialize as a column, a row sum vector x here, and then you start with some product. And what you do is okay, let's go over it. So for every gray code, you first check which bit is changed. Okay, so J is that one. S, if it is changed from 0 to 1 or 1 to 0, because if it is changed from 0 to 1, you need to add the column. If it is changed from 1 to 0, you need to remove the column from the row sums. So this is what it says. And then you do the update operation here on the row sum vector. And then you compute the product and you add it to your permanent value. So that is the algorithm. And we want to do this in parallel, and we want to do this for sparse matrices. So in high performance computing, there are a bunch of, many sparse matrix storage formats. We also use them for graphs. So for instance, we use CRS format for a graph. It is a little bit weird because compressed row storage. So graph doesn't have rows, but this is the name. We are using the same format. And this is the compressed row storage and compressed column storage for the matrix on the left. So what you do is, in fact, really easy. You just store the non-zeros either by going from left to right every time, and whenever you come up to the end of the row, you go back to the other row. And for instance, 7, 5, 1, 3, 1, 10, 4, 5, as you see here. Okay, so this is the you store the rows of the non-zeros of the rows adjacently, in short. And here you store the column IDs of these. So here, this is the first column, this is the third column, this is on the second column, this is on the fourth column. So you have MOM storage here, if you have M non-zeros inside your matrix. And you have additionally an array of size n+1, and they store the starting locations for each row. So this thing shows that location, 0, and this is the start of the first row. This entry shows the start entry for the first row. This is the second row, and this shows it for the third row, for the fourth row, etc., etc. So this is compressed row storage. And when you take the transpose of the matrix and do the same, you obtain compressed column storage. In fact, you can say that we store the non-zeros of the columns adjacently, then we store the row IDs, then we store the starting point for each column. So this is what you do for sparse matrices. And believe me, they are really useful. Because, for instance, we have social networks, and social networks have billions of vertices, but only like maybe 10 billion edges. So you can have billion square entries or edges, possibly, but you only have like 10 billion, okay? So because our graphs are sparse. And without these kind of data structures, it is impossible to deal with that kind of data. So this is coming from a paper from 2019. So what I did is really simple. So the first thing that I did, okay, so there is Ryser algorithm, and there is the gray code optimization on top of it, and it is known in the literature. So what if the matrix is sparse? You can use the sparse storage. And how it is useful, because so if you go back here, you see that there are zeros here, and you don't do zeros. You don't process zeros. You don't do anything for them. In the original algorithm, in this one, we have this 1 to n loop, and you don't need to do it. Okay, you just store the positive ones or the negative ones, non-zero ones, okay? So this is the first thing. So you use RPTRS and the CPTRS when doing computation. So this is the first thing, and this is really simple. And the second thing is the row sums. So especially if you are dealing with graphs, the matrix values are always, I mean, 1. So it's a 0-1 matrix. Adjacency matrices contain zeros and 1. And I realized that in the row sum vectors, some of them, not some of them, in fact, most of them contain at least one zero. So when you have a single zero, only 1 0, the product becomes 0. And that computation is meaningless here. So let me go back to the original algorithm. So that product is meaningless. So what you can do is you can, okay, maybe use the sparse storage formats and do this operation and say now, okay, I saw 1xi, it is 0, then I do an early exit from here because the rest will be the rest is not important. But I realized that, I mean, it is significantly dominant. So the number of cases or gray codes for which you have 0 entries in your row sum matrix, it is really too many. Okay, so you can just count the number of non-zeros inside your matrix, and after that, this n zeros is not non-zero, by the way, it is number of zeros. So whenever I see some 0 inside my row sum matrix, I say, okay, okay, this was previously 0, now it becomes non-zero. Okay, so this is 0. Let me see, there is, yeah, so this became 0 because this is after the update, then I increase the number of zeros. If it is, I mean, if I have if I don't have any zeros inside, then I do the product. Okay, so that's the really simple algorithm. Okay, so this is the algorithm is called Ryser. So there is there is this example here. So the initialization you saw is here, that thing or that thing. We are not changing it. So this is the original one. So you compute the row sum and you subtract the half of it from the last entry. Okay, so the row sum is 2 and 0. This is 0. 0 minus 2 divided by 2 minus 1. So again, this is 2. This is minus 1. This is 3. This time the last entry is 1. So 1 minus 3 divided by 2. Yeah, there is something wrong here. So this should be 0.5, I think. Okay, so again 0.5, and it goes like this. When you, okay, so the first gray code, it changes this thing, the last one. So we update it and we obtain some different values here. And the next gray code, we change the second bit and the second column, sorry, this one here. Again, you update these things. So you add 1 to here, and you obtain zeros. So you don't need to do anything for this row vector. And again for this one, and again for this one, etc., etc. So until now, we have exploited the sparsity. We use sparse data storage, and we omit some of the unnecessary multiplications, which is in fact really useful for many sparse matrices. But one can further omit iterations by explicitly skipping them. So let me go back to the original algorithm again. You don't need to even do every iteration and count the number of non-zeros inside your row sum vector. So you don't need to do that. If you know when the corresponding gray code bit will change. So, let's go back here. Okay, so let's talk about this entry. So this entry here, it is for the second row. Okay, so this row, and it will only change if the corresponding bit for this guy, this column, or this column changes either from 0 to 1 or 1 to 0, right? So otherwise it won't change for these columns. We won't do anything. And this will stay 0. So I can immediately skip these if I can say that, okay, so there is a 0 entry here, and if this bit changes, it doesn't change. If this bit changes, okay, it changed. So what is the minimum gray code that give me the change there? Okay, so that's what I am trying to compute here. And here is the formula I come up with. Probably there is formula similar in the literature. And if you want to check, if you want to compute the value of the jth bit on the jth gray code, then you come up with this formula. And this is a really simple one because every part starts with 0. So this 2 to the j minus 1 comes from that. So if g is smaller than 2 to the j minus 1, then it is 0. We already know it. For instance, for this one, the first half is half of all the gray code. For the 4-bit gray code is 0. For this one, it is 4 bits. For this one, it is 2 bits. For this one, it is 1 bit. And after that, I know the period. So the period is 2 to the j. For the first bit, it is 2. For the second bit, it is 4. So you can compute it. It is really simple. And here is an example. So for the 14th one, it is 1001. And if you apply the formula, you obtain it. Then the next gj be the let that value next gj be the first iteration after the g iteration where gray gj is not equal to gray next gjj. Okay, so I'm trying to find the gray code, the iteration in fact, which my jth bit changes, which changes my jth bit, and that is nice if I have already 0 for that row, okay, for the corresponding row. And here is this is the column, so there is no row here until now, but here gi relates all these things with the columns. So gi is the for the ith row, I compute next gj for every aij, non-zero aij, and I take the minimum of that. So for a row, I have assumed that I have the 0 value in my row sum vector, and it will change. But when one of these bits corresponding to its non-zeros changes, so I take the minimum of that, and I skip until that point. Okay, so this is really, again, a simple idea. And for efficiency, and this is also really important, ordering of rows and columns is important for 2 reasons. Why? First, let's go back again to the gray code and see how many times the first bit changes and how many times the second bit changes. So as you see from here, the first bit changes the most, the second bit changes a little bit less, and then after that a little bit less, and after that the least, the bit which changed the least number of times is the last bit here. Okay, and why it is important? For dense matrices, it doesn't matter. For sparse matrices, it matters, especially for matrices whose degrees, whose number of non-zeros on the columns vary too much, it matters a lot. Why? Because, so suppose that you put you put this one, for instance, this column here, okay, as the last one. By the way, you can order the rows and columns of the matrix, and the permanent doesn't change. So, I mean, you can do that. I mean, it doesn't matter. If you put this guy here, you will do 3 operations per every change of the corresponding bit. But if you put this guy as the last one, then you will do 2 operations per every bit flip. Okay, so this is why it is important. And the number of times they are changing is growing. I mean, 2 to the something, right? So it's exponential. So if you have like a full column, then you want to put it to the first column here on the left, because you only want to process it once, right? And the skip order is a little bit different than that. It also respects to the number of non-zeros inside the columns, but it says also that, okay, I want to have something that that decreases the number of times when I have a okay, so maybe it's better. So, okay, to maximize this value, okay, I am trying to maximize this value with this skip order. So I want to put, for instance, if this row becomes 0 in my row sum vector, then whenever these bits change, it doesn't matter for me. And these bits change frequently. So I want to put these to the leftmost part as much as possible. And this is the idea of the skip order in short. And let's check the results a little bit. So if these are all the algorithms that I implemented. So this is, I implemented them in C++. And this is the natural ordering of the matrix. By the way, these are Erdős-Rényi matrices with where each entry is a non-zero with this much probability. And the size of the matrix is 32 by 32, which is really small. I'm usually interested in matrices with billions of vertices, but for permanent, the problem is different. It's computationally heavy. Data-wise, it is really lightweight. So for this one, for instance, the average time when you use the original algorithm, it takes like 100 seconds. For the natural order, the first algorithm that I showed, which just counts the number of zeros inside your row sum. So this is the execution time for that. And as you see, there is an overhead, and significant overhead, especially when the matrix density is larger. Why? Because then probably you don't have any or not many cases, iterations, gray codes where you have a zero inside the row sum vector. When you order them though, so you are still better up to density 0.4. But if you use skipper, okay, so you still have a good performance for 0.2, maybe 20 seconds, maybe 15 seconds, I don't know. But the overhead increases faster compared to this one because we are trying to compute the minimum GI value every time. And this takes time. But when you order it, it is again much faster because you increase the jumping periods. Okay, so you do this and you obtain better performance even when your density is 0.5. So parallelization. How do we parallelize this? It is really, again, easy. So we have the gray code order here. And what you can do is this, in fact. If you can assign, so this initially looks like an iterative algorithm. So because the next value of the X vector it depends on the previous value of the X vector because you do an addition on top of it, right? So to perform this iteration, you need to perform this iteration. So this doesn't look good in terms for the sake of parallelization. But what you can do is again simple. You can directly jump to that gray code in a really simple step. And after that, compute the rest of the region assigned to you if you are a thread. If you have two threads, for instance, just divide the gray code like this and this. And after that, let the first thread compute that part, the second thread computes that part, and then you sum them up. If you have 4 threads, you have 4 gray code regions, and you do the same. Okay, parallelization is straightforward, but it is not that straightforward because there is some thing here. You don't have a dense matrix. If you assign the gray codes equally like this, and for sparse matrices especially, when you do skipping, some of the threads don't do enough work. So there is a load balance problem here. Because for some gray code regions, maybe we will start from here. We will immediately say that, okay, there is a 0 here. And we will immediately jump to the end of the chunk. And after that, we will say, okay, I am done. But maybe there is a thread working. So if you have K threads or T threads, you don't have T speed up. Okay, so it's not that simple. So this is that version, okay? And this is the speed up with respect to the sequential skipper algorithm with the skip ordering. So as you see, when you have 16 threads, you only have like 6 speed up, 6.1 speed up. If you equally divide the gray code region into 16 and assign one chunk to one thread, okay? So there is immediate remedy in OpenMP. You can use dynamic scheduling. You can increase the number of your chunks so you can make them smaller and assign one to each thread. And whenever a thread is done, it comes and gets another. So this is really one line of code in OpenMP. But that one line of code gives you at minimum 14.4 speed up with 16 threads, which is really good. The efficiency is really good. So you are good. Okay. So for GPUs, again, I mean, the problem is the parallelization is simple because you have independent chunks. You just need to implement the dynamic behavior in a nice way. And for some reasons, that architectural reasons, GPU specific architectural reasons, load balancing among the adjacent 32 threads is important on GPUs, okay? Because we call them a warp, and whenever a thread is done with its work, the other threads wait still for the other one. So you can still implement that dynamic scheduling in a different way this time, maybe a little bit more manual. It's not one line of code, maybe 10, maybe 20 lines of code, but the same strategy, and you can balance the load among GPU threads. By the way, GPUs, probably you know what it can have like 10,000 cores instead of 32, 128 compared to the multi-core CPUs. So what did we have? So this is the sparse, let me see. So we have, okay, this one. So we have the original CPU-based algorithm, the sparse algorithm, and we have the sparse order ring version of it. So it gives us some improvement. By the way, this is log scale, so the improvement is significant. We have the skipper, it gives us a little bit more improvement, and after the skip ordering, more improvement. And GPU Ryser, the GPU-based dense algorithm, is even faster than the sparse algorithm on the GPU, the best one on the CPU, sorry, because GPUs have many threads, cores, sorry, and the parallelization is easy if you add this load balancing part. When you use sparse data structures on the GPU, it becomes much faster. So instead of like 800 seconds, you do it in maybe 2 seconds, maybe 3 seconds. With sequential single core execution, dense algorithm, sorry, not dense, sparse algorithm, but sequential one. And you have this one here. Okay, so GPUs have different memory hierarchy compared to CPU. So we have these streaming multiprocessors on a GPU, single GPU. They are independent from each other. You can consider them as different computation units. And inside them, we have also cores like 192 or 384 cores at each of them. And in terms of memory, so we have the global memory. On a GPU, you can have like 40 gigabyte global memory or I think 80 gigabyte also. And we have a cache, 40 megabyte cache. And we have also something called shared memory per streaming multiprocessor, which is really scarce, by the way. 192 kilobyte. But don't forget, our matrices are small because we want to compute the permanent exactly, and our matrices are small, okay? So we can fit them on this shared memory, unlike the graphs that we were usually working on, like social networks, okay? And we have registers. So registers also can be useful because, again, matrices are really small. So we can store them here. Why storing them here makes sense? Because they are closer to the core, they are much faster to access, they are much faster to read, update, etc., okay? And in this order. So registers are the fastest, shared memory after that, or L1, you can use that part also for any cache, and L2 cache, and after that global memory. And that graph that I shown you was the version, the implementations with global memory. Okay, so maybe it's better I can skip these definitions. I already talked about that. And as you see here, so this is this first lighter bars here. and this is the matrix size, 34 by 34, 35 by 35. So these light bars are the global memory implementations. If you use shared memory, okay, for the X vector, for the row sum vector, not the matrix, then you have again significant speed up, like 25% maybe. By the way, these matrices are small. We should have a bigger case here. Sorry for that. But we are taking the experiments, in fact, now because we are finalizing this study. Shared memory has, again, this is architecture detail. It's banked. So we have banks, memory banks inside shared memory. You can consider them rooms, and there is data inside, and there is only a single door. You go there and you say, okay, give me this data, and one guy goes inside and brings you the data. If you ask too many data, then it will take longer. But if your data is distributed to different rooms, then you will get them at once because you can make each of these guys work in parallel, right? So if you be careful about it, you can obtain a little bit more speed up. Okay, so this third thing is the case, and this is the best algorithm where you store your X inside the shared memory, and you take care of the bank conflicts. This is what we call them. You can also use registers. So usually we don't do these kind of things, but for permanent, it is really simple to do this. So we had a prep with C++ preprocessor working for us to adapt itself for different matrix sizes. And after that, if you store the X in the register, you again obtain significant amount of speed up compared to the best algorithm until now, which is X shared LB, which is the first one here. Okay. Until now, I talked about the execution time, but what about accuracy? We are multiplying numbers, and okay, although the matrix sizes are small, there are 40 of them. So we multiply 40 numbers, row sums, and that's a burden for precision. So because we have limited precision in our computers, I mean, if you want to use C++ and not pure C++, and not external libraries like big number libraries, you need to do it like this, right? So you need to have a fixed amount. You need to have a fixed amount of precision. So how can we overcome that? So we have something called matrix scaling, and this is again from another work from 2015. There is a scaling algorithm. It's called synchron-norm, and we parallelize it on that work. And it is about making a matrix, converting a matrix to a double stochastic form. When I say double stochastic, the row sums are 1 and the column sums are 1. So what you need to have for this is you need to have a row scaling vector and a column scaling vector. And after that, when you multiply each aij with the row scaling vector I, column scaling vector j, and for you do it for each entry, you have the scaled matrix. Okay, so you have this row scaling and column scaling vectors, which are called matrices here, but they are diagonal matrices, so you can implement them as also vectors. So we have this algorithm, we have this lemma. Let A be an n by n01 matrix with total support. So I will talk about it later if time permits, but currently it's not very important. R and C are these scaling vectors, but in this formulation, we want to multiply these like that. So we say that they are diagonal scaling matrices. And this is a double stochastic matrix. And how you obtain them, R and C is here. Okay, so the synchron-norm scaling. There are other scaling, symmetry preserving scaling, other scaling algorithms in the literature, but we like synchron-norm. You have this formula. So permanent of the double stochastic matrix is equal to permanent of the original matrix times the row scaling entries and column scaling entries, the product of row scaling entries and column scaling entries. And to see that it is easy, because what we do for every transversal is we take one entry from each row, one entry from each column. So if you do it for the scaled matrix, you in fact include your row scaling entries once for each transversal, and column scaling entries again once for each transversal. So you are in fact multiplying them. So I will come up to this later if time permits, but so this is important for now. So if I compute the permanent of the scaled matrix, then I can easily go back to the permanent of the original matrix. And synchronous works like that. So here, as you see, I have the matrix here. Okay, so this is the 0, 1 representation of it. And for the first scaling iteration here, I obtain these values. Okay, this is the scaled matrix. This is the second iteration. This is the third iteration, fourth, fifth. And after that, in the last iteration, okay, it is iteration 20. You can go further, but it doesn't improve much because you already have the double stochastic form here. And these are my probabilities now. So I will use them as probabilities in one other work. I will describe it later. But you can see that these two things are large. And I just want to show this relation. So this entry here is in 2 out of 4 permanent, right? Sorry, 2 out of 4 perfect matching. So it contributes to the permanent in 2 ways, and there are 4 ways to contribute, and the value for that entry is 0.5. And this one here, this entry, it contributes to only 1 perfect matching, right? And these values are important, but that will be the content of another work. But I just have this double stochastic form. So why this is important? Because I can, instead of scaling it to 1, I can scale these things to 10 or to 5 or to 4. And then my product of these values will not be too big or too small. So they will stay in the precision. Okay, so this is what we are aiming for. We want to keep the accuracy. So what happened? So we computed we kept everything in 32 bits, including P, including everything in 32 bits, and the matrix in 32 bits also, and also 64 bits. So this thing here, this is the matrix size again. So 30, 31, 32, 33. And there are densities here, you don't see them. This is, I think, density 30, 0.30, density 0.40. And as you see, the original algorithms, let me see. Okay, so these are the 32-bit values. The values here is the ratio of standard deviation divided by the mean of k executions, let's say 50 executions, okay? And as you see, the standard deviation is too much for these things because they are computed in 32-bit. So it's like 10 to the minus 1, and here even 10 to the 2. So, I mean, and as you see, in fact, we don't have a bar for the first thing because we usually get none here, not a number. So that precision, 32-bit precision, is not sufficient for these matrices. And as you see, the accuracy drops. In fact, the error increases significantly when the matrix size increases because we are multiplying more numbers. So that's really simple. And the coefficient of variation, these values are, you can say, okay, they are coefficient of variations, and they are computed with respect to 128-bit result, which is really good, which is really stable. You compute every time the same number, so that's perfect. 64-bit is enough, okay? 64-bit is enough, so that's good. And scaling to 1 reduces the error, so there is some progress here, okay? And so these are smaller matrices. For larger matrices, scaling works a little bit more better compared to this. But as you see, they make the values not a number to numbers, and they reduce the error also. So why do you want to use 32-bit? Because it is faster. So in the computing devices on GPUs, 32-bit performance is faster compared to 64-bit performance. And there is no native 128-bit thing. So probably it's using multiple instructions behind when you use 128-bit data format. It's a native data format, but there are probably multiple architectures, instructions behind it. Okay, so this is the performance. So if you do the same computation with 64-bit, for instance, you have 20 seconds, let's say here, but if you do it with 128-bit, it is 200, 300 seconds. So scaling will work if you have a really, really large permanent in 64 bits. Okay, so that's the idea. And this is the performance, max performance of the GPUs, 32-bit and 64-bit performance. As you see, this is large. Okay, so I have 10 minutes. So I have another set of slides, but let's stop here and ask the questions because they will take more than 15 to 20 minutes. So this is the rest of the talk is supposed to be about the approximation of the permanent when you have larger matrices. So I prepared the slides for that, but let's keep it for the exact computation for them.
Kamer hocam, for your nice presentation. Any questions? It's time to ask questions if you have any. Source code in progress. Okay. Superman. Permanent and Superman.
Yes, so we are really, I mean, we are trying to gather all the codes that we have written for this thing and make a CPU, GPU hybrid permanent computer, exact and approximate. And we call the Superman because of this combination. And this is in progress, but I think they are available now.
So in the lab you use GPU. So do you use any special instruction set from your specific GPU? Or is there exist any such kind of special instruction set? So do you use, for in CPU, as far as I know, there are some instructions set AVX2 and you have some special instruction sets. What about in GPU? Is it really the case again? Can we use some special instruction sets for instance, somehow row multiplication or multiplying 3 elements in advance?
Yeah, for permanence, the computation is easy. In fact, you can consider this AVX instructions as 32 threads working together on a warp, inside the warp for a GPU. So that line is 512-bit, 256-bit operations when you do on CPU correspond to a warp, single warp on the GPU. So you don't have that kind of instructions, but we have they have tensor cores. So we didn't leverage them. We didn't use them. So they are special cores. They can do special things. They can do multiple things at once, which will definitely work for dense matrices, because for dense matrices, you do the same operation, okay? It doesn't matter if you, especially for approximation. So I was thinking approximation, but still, I mean, for dense matrices, you can maybe handle multiple gray codes together, okay, with these tensor cores. Maybe that's possible. But we also use some special architectures like finding the set bit in the gray code. So which bit is changed, which bit is not changed. So we need a function like that. So that's coming also from the, there's a special instruction on the GPU.
So in fact, here you use some ordering. So you ordered your matrices, sparse matrices, so you obtained better results.
Mm-hmm.
So is there any bound, improvement bound? I mean, can we say anything about, so this permanent multiplication cannot be done faster from this upper bound or for lower bound? Is there such kind of a...
It depends on your maximum and minimum degree. So if they are the same ordering, especially sort order, doesn't matter. It won't work. It won't give you a performance boost. But if you have
the number of entries, I'm sorry,
number of entries in a column. So if you compute the number of non-zero entries at each column of the matrix, and if the variance is too much, then sorting will work. And so the cost is, so we know in fact how many times each bit changes in the gray code. So you can compute the exact cost when you sort them. exact number of multiplications, exact number of additions, X vector updates you need to perform by just multiplying the first number of non-zeros with 2 to the n-1, and after that 2 to the n-2, and after 2 to the n-3, and if you add these numbers, you know how many updates you will do on your X vector.
Is there a better ordering? I mean, do you think that there exists a better ordering? Can we?
For Ryser, no, because sorting will give you the minimum number of X updates. For skipper and counting and obtaining these periods, it matters. So skipper ordering is specialized for that. We are trying to improve the extend the length that we skip, extend the number of iterations, adjacent iterations that we want to skip. And sorting is not always the solution for that. But if you only want to minimize the number of updates on the X vector, sorting is the only thing that you can do.
You mean this is best possible, or can we do it better?
For the X vector updates, sorting is the best possible. For the skipper, that's a good question, very interesting question. Maybe there are orderings that we can come up that extends the skipping iterations. They extend the number of skipping iterations, and that's a really nice line of study. I mean, I just come up with skip order with some insights on what I am skipping, what I am not skipping. So there is no theoretical study there, but it can, I mean, there can be.
What is the connection between permanent and graph? So what is the interpretation of permanent in terms of graph theory? Did I miss that?
So what we were doing before is computing the perfect matching, okay? One perfect matching from a graph having millions or billions of vertices, okay? So we wanted to count them. How many perfect matchings do we have? So that's the permanent of the corresponding adjacency matrix. So if you have a bipartite graph, the number of perfect matchings inside that. So let me go back to this slide maybe. The first here. So here, for instance, in this bipartite graph, I have 4 perfect matchings and only 4, not more than that. And the permanent for the 0-1 matrix, 0-1 adjacency matrix corresponding to this bipartite graph is also 4. Because every perfect matching contributes as 1 to permanent.
Perfect matching? What do you mean by perfect matching?
Perfect matching is a set of edges. So here we have set of edges. If you have n by n matrix, you have n edges, where each vertex appears exactly once as an endpoint. So 1 is matched to 6, 2 is matched to 7, 3 is matched to 8, 5 is matched to 9, 4 is matched to 10, for instance. So that's a perfect matching.
Only once.
Mm-hmm. So not every bipartite graph has a perfect matching, and that means that the corresponding adjacency matrix is, I think, yeah, it doesn't have a total support. So probably it is not. Probably it's ranked deficient symbolically, but
number of perfect matchings is permanent.